Hi everyone, welcome back to yet another Euphoria Academia YouTube video, where we do past papers and show you tips and tricks on how you can tackle the papers. Today we're going to be doing the Physical Sciences Paper 1, 2022, which was written in the year 2022 in the May-June exam period. So my name is Ole and I'll be taking you through it, so let's get to it. All right, just to warm up, we're going to do a couple of multiple choice questions that will help us get ready for the main question of today. So, question 1.1 is asking us, or it's telling us that a bucket is at rest, and it's asking which one of the following is the reaction force to the weight of the bucket as described by Newton's third law. So, Newton's third law speaks about action reaction pairs, right? So it speaks about action reaction pairs. So if one force does something, there's an opposite but equal force acting on that force, or the object that is doing that force, right? So the weight of the bucket, that has to do with gravity, right? So that's if let's call it Fg, which is the force of gravity, right? And the force of gravity has something to do with the Earth. All right, so let us go through our options there. So we have the weight of the bucket. So what will be the action reaction pair? Well, we see that all of the, well, not all of them, but two of them have to do with the Earth. So will it be the force of the table on the Earth? No, we're speaking about the bucket here. So essentially, it will be the force of the bucket on the Earth. So B is our answer. And then for 1.2, a ball is dropped from a small height above the ground. All right, so let's quickly draw that situation. So we have a ball at some height here, and then it is dropped from a small height above the ground. So let's just call this the small height h. All right, and we need to ignore air resistance. That means this ball is in free fall. The following pairs shows physical quantities associated with the ball while it is falling to the ground. In which one of these pairs will both quantities change while the ball is falling? All right, so as the ball falls, all right, which quantities are changing? Well, we'll just look at velocity. All right, so we know that as it falls, because it's being accelerated by the force of gravity down, let's just call that AY, that our velocity will increase. All right, now which quantities have to do with velocity? Well, momentum as well as kinetic energy. All right, because I'm just looking at the physical quantity that's changing, which is velocity. So that's just me giving you the answer actually, because we will see that kinetic energy and momentum is part of the option set. So because velocity is changing and it's the only thing that's changing, that will be our answer: kinetic energy and momentum. Mechanical energy does change. Well, not really actually, because it goes from potential energy to kinetic energy. So the physical quantity of it does not change. The weight is constant. Gravitational acceleration is constant. And then gravitational potential energy does change, but the gravitational force does not. So our only correct answer is B. Right, now to the main part of this question, which is question 2. Question 2 has to do with a bit of Newton's laws, and we'll get into it. But it's a question that starts from question 2.1 and ends at question 2.5 and is a maximum of 17 marks. So let's get into it. Right, so let's just speak about this question and talk about what's going on. and then we'll explain it in more detail in the next slide. All right, so we have a man facing difficulty swimming in a dam. Why is he swimming in a dam? During the rescue operation, an inflated tube attached to a helicopter by a rope is dropped from the helicopter. The man of mass 70 kilograms, that's important, holds onto the inflated tube of mass 4 kilograms while the helicopter is flying horizontally at a constant speed. All right, an average frictional force of 300 newtons is exerted on the man-tube combination while they are dragged horizontally. All right, along the surface of the water by the helicopter, the rope makes an angle of 50 degrees with the surface of the water as shown. Assume the rope is inextensible and massless. That means we're going to be looking for, it doesn't increase in size, it doesn't shrink, it doesn't stretch. So we know that whatever force is on the helicopter is the force on the man. So that means we'll be looking for tension, right? And the water of the dam does not flow. That's very important because it essentially means that at this point in time, the only force on this man as he's being dragged across the water is not, there's no force of the water on the man, but rather it's just the friction that was mentioned before. All right, so that's just what this means. Okay, so let's look at the questions and let's get into it. Right, so let's see exactly what is happening. So we have a man swimming, yelling for help, and he is being pulled by a helicopter moving at a constant speed to the left, while there is tension in this rope, and this tension will be pulling in this direction in reference to the man, while the man is being or feeling the force of friction in the horizontal direction, and the water is just keeping him up, and we have some gravity on this man, and that's essentially our situation. So let us do the question. All right, question 2.1 has to do with stating Newton's first law. Now, Newton's first law, sorry, fighting with English today. A body will remain in its state of rest or motion at a constant velocity unless acted on by an unbalanced force. And that's our definition of the first law in words, right? Now for question 2.2, we're asked to draw a free body diagram of the man-tube combination while they are being dragged. Now, we already told the forces and we already demonstrated what is happening. So at this point, it should be easy to determine what the forces on this man-tube combination is. I'm just gonna draw a block to represent the man and tube combination. So we're going to have the weight acting on them. We're going to have some sort of normal force. When you study physics longer, you'll see that this normal force is actually the buoyancy, so the thing that's keeping them above the water. And then we are told that there's a constant friction, right? And friction always acts parallel to the surface, and it's Fk because they are moving. and we're going to have the force of tension in this direction at an angle. And that's our free body diagram. For question 2.3, we're asked to find the tension. Alright, so we're going to look for our forces in the x direction. Alright, so we're going to compute the sum of forces in the x direction because of the rope is at an angle of 50 degrees. So that means we're going to have components of the tension in the y direction, as well as the tension in the x direction. All right, so because there's just many calculations associated with the y direction, we only have tension in the x direction as well as friction in the x direction. So it makes it easy to compute forces in the x direction. All right. And we are told that the helicopter is moving at constant velocity, which means the man is also moving at constant velocity because the water is not flowing in this case. So if we have a constant velocity, that means the sum of our forces will be 0. All right. So we have a situation where the tension, the rope, is at 50 degrees to the horizontal. All right. That's our tension force. So we need to find this component, the x component. All right. And because we're computing our forces in the x direction. Now, we know that in this case, to find our x component is going to give us a situation where Tx is going to be equal to the magnitude of our tension multiplied to cos 50 degrees. And that's trigonometry right there. All right. And then let's just compute our forces here. So we will take our left hand side as positive, right? So that will mean that our tension acting in the x direction is positive minus our frictional force is equal to 0, right? This is just substituting what we have here. Okay, now we already said our Tx is T cos 50 degrees, and we are told that we have a constant frictional force of 300 newtons, and that is equal to 0. And once you do some maths, we will find that our tension is equal to 466.72 newtons. All right, and that's our answer. All right, for question 2.4, we are asked that how will the answer to question 2.3 change if the helicopter accelerates, if there is some sort of net acceleration of the helicopter while it's dragging the man. The frictional force and the angle between the rope and the surface of the water will remain the same. All right, so we will essentially have a situation where the F net is not going to be equal to 0 because there will be some acceleration, right? So our F net will be equal to the mass of this man tube combination multiplied by some acceleration, all right? And then if we have a situation like that, let's just compute our forces. Our forces are still the same. Nothing has really changed except the fact that the helicopter is now accelerating. So we're going to have our Tx minusing our Fk, and that will be equal to our mass times acceleration. All right. So that would mean our tension, in this case, our Tx, will be, or let's just compute the actual tension from what we had before. All right, let's just compute the actual tension from what we had before. All right, our tension will then be equal to our MA plus our FK divided by our cos 50. All right, that will be our equation for this situation. So I'll just put a subscript A for acceleration. So our TA, will it be larger or smaller than our initial one without acceleration? So our T naught, when we didn't have acceleration, is equal to our Fk divided by our cos 50 degrees. Now we can see that because we don't have MA added to the numerator here, it will look like, or it is, that our TA will be larger than our T naught. Therefore, our um okay, yeah, our answer for our tension will T will increase. That's uh that's exactly the situation that we have. For question 2.5, we're told that in another rescue operation, the inflated tube of mass 4 kilograms is dropped from the stationary helicopter and it strikes the water at a speed of 16 meters per second. All right, the tube sinks vertically downwards into the water to a depth of 0.8 meters, then rises to the surface. The rope hangs loosely. That means there is no tension. There's nothing that's restricting this motion, which kind of alludes to what we're going to speak about, which is free fall. We have a situation where there's free fall to some extent through the water as well as when it rises up again. Well, as the tube is thrown from the helicopter and into the water, floats down to a height of 0.8 meters, then floats back up. I like to think of it as, have you ever thrown something into a glass of water? Maybe you've thrown ice or you've thrown whatever, and it exhibits this type of motion where it goes to some depth and then comes back up to the surface again. And I have an animation that can show us. So think of it as it's shooting through the water, coming down through the water like this apple. And as the apple gets to this depth, let's just call that depth. Let's just assume that this is our tube and it shoots through the water and it comes to a depth of 0.8 meters. Let's just call that 0.8 meters. And then what eventually ends up happening is the fact that our apple will float back up to the surface. All right. So in this situation, we initially had a velocity of about 16 meters per second. So let's just write that down. We had an initial velocity of 16 meters per second. All right. And then once it got down to the height of 0.8 meters, we can even see in the animation that our, let's just call this V final. Yes, our V final was 0 because it stopped. It stopped, and as it stops, right, and it floats back up to the surface. So this is essentially the situation that we have. All right, and in this situation, all right, it slows as it gets to our VF of 0, and yeah, that's the situation. All right, so let's do the question. Now, question 2.5 is asking us to calculate the magnitude of the average upward force exerted on the inflated tube while it is sinking. Right, so we have to calculate while it's sinking. So it's already through the water, it's already pierced the surface of the water, and yeah, we have to assume that the average upward force is constant for the motion. Now that's very important, right? So while it is shooting through the water, we have a situation where we have a constant downward force, and yeah, we have a constant downward force, and this constant downward force is actually the force of gravity. That's the only thing acting on this tube. And then we are told that we have a constant upward force of the water, constant upward force, right? And that is the force of water. Now, if we have a situation like that, we have constant force, constant upward force, right? Is this not a situation where we can evoke our kinematic equations? Because our kinematic equations look at a situation where we have a constant acceleration, and then we have velocities I and Vf at certain points in the motion of this thing accelerating. All right, so let us quickly draw a free body diagram of what exactly is happening to our tube while it is sinking through the water. All right, so we have the force of gravity, as we already said, which is the weight. We have our weight on this tube, as well as the constant force of the water, right? Constant upward force of the water, and we have a VI of 16 meters per second. And then while this thing is dropping through the water to a height of 0.8 meters, at this 0.8 meters, we're going to have a V final of 0 meters per second. All right, so as we already established, we're going to be using our kinematic equations while it's paired with our Newton equations. Using our Newton's laws, or second law, we know that F net is equal to our mass times our acceleration, and we will take our upward direction as positive, where we have the force of water minus the force of gravity being equal to the mass multiplied to the acceleration. All right, so we already know that our force of gravity, we can compute it. So let's just substitute that into our formula, minus 4 kilograms of the tube multiplied to 9.8, and that is going to give us m is still 4, and we don't know our acceleration a. All right, so we're going to use our kinematic equations, where we have our Vf squared being equal to our Vi squared plus our 2a delta y. All right, because we're trying to find our equation for, we're trying to find our acceleration so that we can substitute it into this formula. We'll just call that equation 1, and this will be equation 2, so we can find our force of water. Right, now our final VF, right, as it's sinking, right, we already established that it's going to be 0, and our VI is going to be minus 16, right, because we took upward as positive, and this VI is essentially pointing downwards, right? So we're going to square that plus our 2. We're trying to find our acceleration. Now our delta y, we're moving from 0 meters minus 0.8 meters. That's our delta, because we go down 0.8 meters, and as established, we took up as positive. All right, so while we do some maths, we're going to find that our acceleration is going to give us 160 meters per second squared. Let me just quickly check these calculations. Yes, that should be the answer that we do get, because we're going to take this to the left hand side. It's going to give us a negative. Okay, that is correct. All right, so we're going to substitute our result of A equaling 160 meters per second squared into our equation 1, and we're going to find that our force of water is going to give us an amount of 679.2 newtons. And that's our question.